Good morning, guys. So this morning is the 16th of March 2020, and I suppose I would just like to begin by wishing you all well and wishing those you care about are well. This morning's lesson will have two main parts. The first will be a recap, and the second part will be the new stuff, and it's going to be on rates of change. So for you guys, this word change is going to be important. So we're going to see how one thing changing affects another thing changing. You already have the skills necessary to do this, you just don't have the concept. So this is going to be conceptual. The recap will be the recap of what we did on Friday, which was max and min. And the recap will take the form now of answering question 7 from the assigned homework. So find the coordinates of the two turning points of the function in numbers 3 to 8 and state if each turning point is a local maximum or a local minimum. So the first job at question 7 was to find the points at which it's a local maximum and local minimum. So let's take a look at that now. So our first task was to find out the local maximum and local minimum points of this function. So from the learning the last day, we know that at a local max or a local min, the slope at those points will be 0. So the slope of tangents at maximum and minimum will be 0. So we can use that fact because from this function up here, I can get a function for slope. So what do I have to do to this function to turn into a function that deals with slope? Yeah, so I'm going to have to differentiate this function. So because we have a y here, I'm going to use the notation dy dx is equal to, so when I differentiate this, I go 3 bracket 2x to the power 2 minus 2 bracket 9x to the power 1 plus 12, and we can tidy that up to be 6x squared minus 18x plus 12. So that's slopes are equal to that. So that's a formula for all of the slopes. But we want to know a specific slope. We want to know when the slope is equal to 0. So I'm going to let this equal to 0. And so I now have an equation, 6x squared minus 18x plus 12. So I now have an equation. So I now need to find out when is this equation equal to 0. But what sort of equation is this? There's a little hint there for you. So what sort of equation is 6x squared minus 18x plus 12? Yeah, exactly. It's a quadratic equation. So to solve quadratic equations, probably the handiest thing to do might be just to bash it into the minus b formula. So we're going to put this information here into x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So it's bbaca. So b is minus 18. Minus 18, 6, 12, 6. And I can put that into my calculator. So I go fraction. And then I go minus bracket minus 18 plus the square root of minus 18 squared minus 4 bracket 6 bracket 1, 2, close bracket downstairs 2 bracket 6. So I put it into my calculator, hit equals. So I know that there's a maximum or a minimum at x equals 2 or at x equals. So that was the positive version in here. So now let's scroll back into it until we change that positive to a negative. And we get x equals 1. So I now know that at x equals 2, there's a maximum or a minimum, and I know that at x equals 1, there's a maximum or a minimum. So how can I check to see if this is a maximum or a minimum? Probably the handiest thing to do would be to work out the y values. So let's take a look at the y values. So we go 2 bracket 2 cubed minus 9 bracket 2 squared plus 12 bracket 2, and that's what y is equal to, and we get that from up here. Sorry, you can't see that. We get that from the original function up here. I might be able to get both on the screen there. So y is equal to this thing here, and we also have y is equal to this thing here. So doing the substitution, we get this. So we now get y is equal to 2 bracket 2 cubed minus 9 bracket 2 squared plus 12 bracket 2, and that's going to equal 4. So this corresponds to the coordinates 2, 4, and over here we have y is equal to 2 bracket 1 cubed minus 9 bracket 1 squared plus 12 bracket 1. So y is equal to y is equal to 5. So this corresponds to the point 1, 5. And that means that this will be the minimum and this will be the maximum, because this value is smaller. Now, this approach is not strictly the correct approach, but it's good enough for us. Okay, so on to today's new stuff, and it's going to be rates of change. Okay, and to start this, let's say we have an object down here somewhere, and I give that object a push, and I push it over to here. So we could think about this in terms of coordinate geometry, that two things have changed. Its height has changed, so that will be that distance there, and we're going to call that distance there the rise. So that's the change in height, and that we call that the rise, and then we can change the proximity of it, so we're going to call that the run. And if we want to compare these two, we want to look at the rate at which the rise is changing for every unit of run. So we would look at rise over run, and that will be rate of change. So the rate of change is the same thing as rise over run. Now we know that rise over run from stuff we did maybe last year, rise over run, that's the exact same thing as slope. So this kind of links in with what we were doing recently, and we know that slope, well, that's the same thing when we're talking about functions, it's the same thing as dy dx, or f prime x. So when we are differentiating, we're finding slope. When we're finding slope, we're finding rise over run. We're finding rise over run, we're finding rates of change. So what I need you guys to be able to do is form a link between differentiating and finding rates of change. So if you're asked to find the rate of change of something, that means we have to differentiate it. Okay, so that's really the concept that we need to grasp today. If we want to find how quickly something is changing with respect to something else, i.e. its rate of change, that means we differentiate it. So just a quick look at notation. So I just told you there that rate of change means differentiate. Okay, rate of change means differentiate. Rate of change means change in height divided by change in, I called it proximity. And that equals differentiate. Still, okay, so we're getting to where we need to be. Sorry about all these words. Now, the change in heights, well, that's the difference between the heights, so that's going to be y2 minus y1. And we know this anyway because we're talking about the slope, so it's going to be x2 minus x1. That's the distance, that's the change in how far something is. That's the run, and that's the change in the heights, the rise. So y2 minus y1 over x2 minus x1. Now, that's the same thing as dy dx, okay? So it's the change in the y's divided by the changes in the x's, dy dx. Now, that makes sense when we have y's and x's, but sometimes we may not have y's and x's. We might have, let's say, area is equal to pi r squared. When we have that, yeah, well, the or, let's see what happens to the circle as we make the radius bigger. So we would have the changes in the or, so we'd have r2 minus r1 on the bottom. We would have a2 minus a1 on the top. Okay, so if we have that, we would then have dA dr. So this is just notation. Don't be too concerned about this, but it's nice to have some understanding of why we're changing these letters here. It's because the way the function was given to us in terms of different letters. Okay, if we want to look at Newton's notation for this, he might have written something along these lines. Bracket or. So the function a of or is equal to pi r squared. And then to show that we're differentiating this, we would go a prime or is equal to 2 pi r. So if my recent discussion about notation has set you to sleep, wake up now. This tends to be how this topic is examined in the Leaving Cert. And it tends to be examined on the basis that there are two facts. The first one, the rate of change of distance with respect to time is speed. The rate of change of distance with respect to time is speed. Our second fact is the rate of change of speed with respect to time is acceleration. Now, there are some words in here that are really, really important. The rate of change of distance with respect to speed, the rate of change of distance with respect to time is speed. Okay, now, for those of you who are doing science, you probably call distance displacement, and you probably call speed velocity. So those words do exist. Distance means the same thing as displacement. It would be unusual at Leaving Cert ordinary level to use the word displacement for that, but they could. Displacement. And speed, we would tend to call that velocity if we're being really, really strict. So that tends to be velocity. The idea of time and acceleration, they're the scientific words, so we're okay with them, okay? Now, I don't see them using those words, but they could use the word displacement and they could use the word velocity. So just be aware of that. So we're going to call this guy here fact 1. That's a nasty looking one. And fact 2. So fact 1 is the rate of change of distance with respect to time is speed. Fact 2 is the rate of change of speed with respect to time is acceleration. Okay, you can really think about that as my distance changes, for every unit of time that it changes, that is my speed, right? And we can think about that, how quickly my speed is changing. Well, that's just acceleration. So these facts should kind of make sense to you. But realistically, you're fine if you just remember them. It's kind of a flow chart. We'll talk about the flow chart now. So based on the previous clip, we have talked about that speed is the rate of change of distance with respect to time. And we know that when we see this rate of change thing occurring, that means we're differentiating. So if we differentiate a formula for distance, we get a formula for speed. So to get a formula for speed, we differentiate a formula for distance. So we were given this question here: a body moves s meters in t seconds such that s is equal to 2t squared minus 4t plus 4. Find the body's speed after 5 seconds. So this is a formula for distance. So according to our previous learning just there, that to turn that formula for distance into a formula for speed, we have to differentiate this formula. So if s is equal to 2t squared minus 4t plus 4, that's the formula for distance that we were given. But we're looking for a formula for speed, so we're going to have to differentiate this guy. So we write out ds dt, and when we differentiate this, we get 4t minus 4. And specifically, we wanted to know what's the speed after 5 seconds. So to find speed after 5 seconds, well, we're just going to let t equal 5 here. So that's 4 bracket 5 minus 4, which is equal to 16. So the speed after 5 seconds is 16 meters per second. Okay, so this is kind of an exam standard question on the same stuff. So just read through that now yourselves. So I'm going to be getting rid of this in a second, moving it to one side. So you might just maybe take it down or take a picture of your screen just so you can look at it while I'm working through it. So it's coming down in 5, 4, 3, 2, 1. Okay, so let's put that to one side and let's start working through it. Maybe I'll just read through it myself. Okay, as soon as it touches down, an airplane applies its brakes. The distance s, which the plane has travelled along the runway at any subsequent time t, is given by the function. That's the function there, where s is measured in meters and t is measured in seconds. So that's a function for distance. That thing there, that's all to do with distance. Okay, so t is time and s is going to be distance. And that's using the other notation, not the y equals, but the f of x equals s of t is equal to. Excuse me. So let's take a look at this first question. The distance travelled after 10 seconds. So we have this function, s of t is equal to 200 t minus 4t squared. Now, that's our function for distance. And we want to know the distance when t is equal to 10. So we are not interested in speed yet, we are only interested in distance. So I simply want to know what s is when t becomes 10. So s of 10 will equal 200 times 10 minus 4 times 10 squared. And I can put that into my calculator, and I will get 200 bracket 10 minus 4 bracket 10 squared equals, so that's 1,600. So that's going to be measured in meters, by the way. So that's over 1.5 kilometers in 10 seconds. So that's pretty quick. And that kind of leads us on to the next question, which is the plane's speed. So the second question was the plane's speed. So this was a formula for distance. So what do I have to do to this formula to turn into a formula for speed? So that's a formula for distance. What do I have to do to the formula for distance to turn into a formula for speed? I'll bring back up this fact here. Speed is the rate of change of distance with respect to time. So to get a formula for speed, we differentiate a formula for distance. So we're going to differentiate this guy up here. So if we differentiate a formula for distance, we get a formula for speed. So s prime of t will equal 200 minus 8t. So that's a formula for speed. And so we answered that question there. So that sounded an awful lot worse than it actually was. It was just a very simple differentiating question, but it's wrapped up in this idea of rates of change. Then we're asked the speed of the plane at t equals 10. So at 10 seconds, what's the speed? So that's a formula for distance, that's a formula for speed. So into which of these two formulas, if I'm looking for speed, will I put my 10 this time? Good, so that's a formula for distance, so I won't use that one, I'll use the formula for speed. So s prime of 10 is equal to 200 minus 8 bracket 10, so that's going to equal 200 minus 80, which is 120. So the speed at 10 seconds is 120 meters per second per second. Okay, so that's all pretty straightforward. They kind of gave us numbers, we had to put them into formulas. Good. Now, the next question here. The plane's speed as it touches down. So let's just read this question again. As soon as it touches down, an airplane applies its brakes. So this formula here begins as soon as the plane touches down. So plane speed as it touches down. So how many seconds have passed when the plane touches down? So the formula starts working when the plane touches down. So at the moment the plane touches down, how many seconds have passed? Good, yeah, so 0 seconds. So I'm going to find s of 0. And that's going to give me 200. So the moment that the plane touches down, the speed will be 200. Now, the last question, the time at which the plane comes to rest. The time at which the plane comes to rest. So I'll just get my two formulas written out on a fresh page. We can go as far as there. So so this is the formula for distance. This is going to be a formula for speed. S of t is equal to 200 t minus 4t squared. S prime of t is equal to 200 minus 8t. Now, I want to know the time at which the plane comes to rest. So when it comes to rest, what speed is it doing? So if something is at rest, what's its speed? Yes. So when an object is at rest, its speed is 0. So we want to know, when does the speed become 0? So when is 200 minus 8t. When is that thing equal to 0? That's pretty straightforward. That's just 200 is equal to 8t. So t is equal to 200 all over 8. So t is equal to 25. So it takes 25 seconds for the airplane to come to rest. So the crux of today's learning was, if you're given a formula for distance, okay, we differentiate it and we get a formula for speed. So when we differentiate a formula for distance, we get a formula for speed, so differentiate. Now your book goes into a lot more detail about this process, but for us, that will be okay. So if we have a formula for distance, if we differentiate it, we get a formula for speed. I'm now going to assign you 2 questions to do as exercise for tonight. So I will upload 2 questions onto Edmodo for exercise tonight. So 2 questions on Edmodo. I'll do both of these questions on Wednesday, but have a go at them yourselves tonight and tomorrow. And I suppose, guys, yeah, stay safe.